Okay, welcome to Cosmology, Mass and Energy 1, where I talk about the universe as a whole and what kind of mass and energy you would find in it. This is sort of this number 1 is a setup for number 2, where I do a roll call of all the mass and energy in the universe, but you should probably see this one first so we can get through some background stuff. So first of all, you've stumbled onto Extraordinary Concepts in Physics. I am Robert Nemeroff, and this is Michigan Tech. And we are going through some of the cool concepts in physics, and you're invited to come along. So in standard general relativistic cosmology, the cosmology is too complicated. Einstein created a theory of gravity called general relativity, which was very complicated, which is very sophisticated. In order to understand the universe as a whole, people came up with ways of simplifying it into relatively few variables, and some of these people are Friedman, Robertson, and Walker, and they created the Friedman-Robertson-Walker metric, which includes a standard set of assumptions, and you can then create metrics, which means how time and space are measured between different points in space. So this lecture and the next lecture will be based upon my article, which appeared in the American Journal of Physics, called Adventures in Friedman Cosmology, a Detailed Expansion of the Cosmological Friedman Equations, which you can get to by clicking on this link right there, and it gives you even more details than you probably would have wanted. So the Friedman equations basically talk about two aspects of the universe. One is the scale factor of the universe, A, and the other is omega, which is an energy density in the universe. So mass, like you and me, we're just chunks of matter, and we can be converted into energy by E equals mc squared at any point, but we have some kind of density. And so our average density, the average density of humans or baryons, is some number. And it is one of the different types of energy densities that could exist in the universe. So these two things battle it out in the Friedman equations, and which is consistent with general relativity. What I would usually do is assume the universe is dominated by one type of mass energy, and not several types. If several types are interacting at the same time, they can be quite complicated. And is useful for making detailed predictions about the universe, but is not always as useful for explaining the universe and how it is in different phases dominated by different energies. Okay, so acceleration. There's two different Friedman equations. One is sometimes called the energy equation. One is called the acceleration equation. So the one equation, the energy equation, is the one that I'm following most closely. It only involves A, which is the scale factor of the universe, which you might think of as the average distances between galaxies. Even when there weren't galaxies, you can think, well, where would the galaxies have been? Maybe if you go early in the universe, it would be the average distance between particles. The energy equation talks about A and the time derivative of A. For the energy Friedman equation, the acceleration Friedman equation gets into the next derivative, but they're actually equivalent, and they're all parts of the same, what's called a 4 vector. So you don't have to know the details of what that means. You can look it up if you want. One important aspect for all of this is there are things called cosmic rest frames, which some people call very strange, because special relativity has people moving at different speeds, constant speeds, and there is no special frame. That's why it's relative. Motion is relative. But in cosmology, there are cosmic rest frames. How can that be? Isn't general relativity just an extrapolation of special relativity? Well, it is. But in general relativity, things can happen all over the universe, like the microwave background. And as we saw in another lecture, the microwave background can be hotter in one direction than another. And so if you want that radiation to be the same temperature in all directions, that defines a rest frame at that space-time point. And if you go to another point, you better stop, and the way you know you're stopped is that you look at the different backgrounds of energy, which radiation is a good one, so you look at the microwave background and you say, okay, when the microwave background is the same temperature in all directions, then I'm at rest at that part of the universe. And that's completely consistent with general relativity. There's also things called an event horizon, inside of which events cannot affect outside. There's also something called the particle horizon, which is sometimes known as the cosmological horizon, which is the furthest distances that particles can reach you if they left at the Big Bang. I like to think of something called a gravitational horizon, which is the furthest distance that gravity can reach you. I've got a lot of slides here, so I'm going to press on. Back to the scale factor A, as I said before, a good way to visualize A is the average distance between galaxies, even when there are no galaxies. So in the expanding universe, A is continually increasing in time. So it might be, if the universe is higher average density than flat, that the universe may one day stop and recontract on itself. In that case, you would have not an expanding universe, but a contracting universe, at which point there could be something called a big crunch at the end. And we'll get to that too. But currently, the universe is expanding, so we consider that A increases with time. This is the standard Friedmann equation given in your average textbook. Things that go into this are Hubble's parameter, sometimes called Hubble's constant, but if you get outside the local universe, it actually changes. G is the same gravitational constant that you see in Newton's law of gravity. Rho is an energy density, sometimes will be given as omega when compared to a certain canonical energy density, which is needed to make the universe flat. C is the speed of light. R is an unnormalized universe scale factor, and K, which will disappear as a dimensionless factor related to curvature. So the different types of energies can be added up. So we have mass energy, like you and me. We're mass. That would be one factor here. And we would be changing as the universe expands with like a to the minus n. So n would be 3 for mass energy. For radiation, that would be another kind of energy density that's not exactly like you and me, and then n would be 4. So what happens is we'll go through the roll call of all the stable energy forms next lecture, but the total amount of mass energy in the universe is the total omega, which is rho divided by rho constant, by rho, a rho that's well known, is phantom energy, how much there is phantom energy. We'll get into that next lecture. Cosmological constant, domain walls, what are those? Cosmic strings, matter, which we're familiar with, radiation, which we're familiar with, and ultralight, which actually hadn't been discussed outside of this before. But the total energy is the sum of all of those. They all contribute to the universe. So the Friedmann equation then comes to a very simple form. Sorry for all the math. H, which is related to A dot over A, which tells the scale factor of the universe and how the scale factor of the universe is changing, is then equal to this stuff here, which is the density of phantom energy in the universe times A to the minus n, the cosmological constant times A, which says that as the universe expands, the cosmological density doesn't change. Domain walls, they dilute as the universe expands. Cosmic strings dilute. This is a curvature term. That gets into some explanation we won't give too much here. Matter dilutes as the 3 spatial dimensions cubed. So as the universe expands, matter becomes less dense. Not because you and I become less dense, but because the distance between the average galaxies increases in all the 3 spatial dimensions, so it goes down as rho cubed. Radiation not only becomes less abundant, but also every photon will redshift and become less energetic, and then ultralight does that even more. We have to consider, so the universe is too complicated to really deal with. So we pay astrophysicists and cosmologists to simplify things and tell us what the answer is. And it's hard to simplify things, but you have to assume the universe is the same everywhere in order to really go places with the equations and understand how the universe might evolve, which is usually a pretty good assumption. So the density is still there. So the way they do that is we consider all of these kinds of mass energies to be perfect fluids. Perfect fluids are very simple to deal with in mathematical contexts, so we can make predictions with them. They only have 2 characteristics. They have density, which is the same everywhere, and pressure, which is the same everywhere. And the ratio is related to something called W, which tells you what kind of perfect fluid you're dealing with. Okay, here's the exact amount. W is equal to P pressure over rho density, and you got to throw in a c² if you want your units to work out. So each perfect fluid is a different type of energy. Each perfect fluid will also dilute in a different way as the universe expands. So if you're going to have some kind of strange non-perfect fluid, yes, you can get different kinds of dependencies. You can create universes that do anything you like practically. But we have reason to believe that perfect fluids are a good approximation for these things, and so we track how they evolve with the universe. So here again, I'll go down next time I'll go into details into each of these. If W is less than 1, you have a very strange kind of energy called phantom energy, which is debated as to whether this kind of energy can even exist. This is the kind of energy that is repulsive gravitationally, permeates the universe, but its energy density increases as the universe expands. So ultimately, we will see phantom energy could make what's called a big rip, an end of the universe, where even the phantom energy inside of you and me is so great, it exceeds the amount of our molecules to hold together, and we explode. That's what happened in the future of a phantom energy universe. Cosmological constant universe wouldn't have that fate. It would end differently. A different kind of energies, domain walls, then cosmic strings. At this point, you then have, these are your stable forms that are dark energies. And these are your light energies that include matter, radiation, and ultralight. These have, energy is not conserved in the universe. Matter, particularly, will dilute everywhere in the universe. So there is no place for the energy to go, which is why energy is not conserved. And last, these energy forms interact differently with each other. We're used to two pieces of matter attracting. And that gravity is always attractive. Yet all I'm talking about here is gravitational force. All of this is gravity and only gravity. We're not talking about the strong nuclear force here. But if you have phantom energy will repel other phantom energy. It will repel domain walls, and I'll tell you about that next lecture. Domain cosmic strings, it'll repel particle matter, or it'll repel radiation. It just repels. It's very repulsive and will destroy the universe. However, you can pick other things. For instance, matter. Matter will be repelled from phantom energy and repelled from a cosmological constant, repelled from domain walls, and it will not be attracted or repelled from cosmic strings. It will attract to other matter and it will attract to radiation. One interesting thing is that radiation actually has greater gravitational attraction than matter. Not well known. And at the bottom is ultralight. So these are the strange forms of energy that could exist in our universe, that are perfect fluids so far as we know. And there are possibly fields in the universe that are different from these, but these are stable energy forms, we think. And with that, I will talk about how they evolve specifically each time, next time as the universe evolves, and what the future and past of the universe might be in very simple terms, in terms of the energy forms that were there. Until then, I'll see you next time.